Hello, I'm Todd Colley, President at LSI Chemical. Thank you for joining us today for our presentation at the annual STLE meeting. Today our presentation will be reviewing the performance of permanently suspended nanocarbons in lubricants. I will present first, followed by Chris Gabrelchek, our CEO, and then Kevin Adams, our Vice President of R&D. Today's agenda will be nanotechnology overview, followed by nanotechnology suspension issues solved, nanotechnology clarity issues solved, laboratory testing review, and finally, real-world testing review. We have known for years nano-sized materials have been effective in enhancing lubricants. And as you can see from this slide, there's also a history of presentations here at the STLE and in general publications. There's been numerous issues with nanotechnology in the industry. The particles have not stayed in suspension. They've often been dark in color, and as a result, this changed the final appearance of the lubricants. They also had a very high material cost. These problems have led to limited use across the industry. You will now hear from Chris Gabrelchek, our CEO, about how these issues have been solved.
Thanks, Todd. With our new technology, we've been able to keep nanomaterials suspended indefinitely with excellent dispersibility and having no signs of stability issues for over 5 years. This involved 4 different patents and products from several different companies. It is highly dispersive in Group 1, Group 2, Group 3, and Group 4 base oils. We've had some luck with Group 5 base oils, but in some cases, it causes the nanos to fall out. We've also tested in engine oils, gear oils, and hydraulic oils with the same level of success. This slide shows photos of the different oils that we talked about. As you can see, there's no visible signs of the product settling out, and it's not changed the clarity or the transparency of the oil. In this comparison video, you can see older nanotechnology versus the newer technology. As you can see, the older technology on the right settles out over time, where the newer technology stays completely suspended. One of the things that we've uncovered in our research is that nanoparticles smaller than 10 nanometers cannot be seen because they don't reflect light. This leaves the finished lubricants virtually unchanged, and it also gives us promising results without changing the color of the finished lubricant. We sent the product out for clarity testing. As you can see, the Group 3 synthetic base oil is unchanged once the 5% nano solution is put into it. They both are number 2 on the color scale. They also received a rating of 1 on the Hayes scale, the treated and untreated base oil, so there's no change visibly to the oil. As mentioned earlier, one of the drawbacks of nanomaterials is the high cost. With the new nanotechnology, we're able to achieve the same results at 1/20th of the treat rate. This makes nanomaterials more available commercially. I would like to hand it over to Kevin Adams to discuss our laboratory findings.
Thanks, Chris. Following is the main test equipment that was used to evaluate the nanolubricants. The first is a 4-ball tester, which even though it's most known for extreme pressure testing in greases, it has become the standard by which a lot of lubricants are compared. The second is an HFRR. We chose this method because it gives us a picture of what's happening in the boundary lubrication regime, and also because some white papers have been written that demonstrate the merits of using this technique to predict fuel economy effects in passenger car motor oil. The third is a mini traction machine. This versatile machine gives us the ability to understand film thickness and also the coefficient of friction in the mixed lubrication regime. It has also demonstrated its merits as an indicator to real-world conditions to a passenger car motor oil. Following is the litany of tests that we use for the Phase 1 evaluation of the nanolubricant. With the 4-ball machine, we use 3 different test methods: the 4172A and B, and also the D2266. The 4-ball produced wear scar data and coefficient of friction data. The HFRR was used to also give us wear scar and coefficient of friction data in the boundary lubrication regime. And then lastly, the MTM was used to determine coefficient of friction in the mixed regime. In addition, we tested clarity using the Hayes test and thermal conductivity using the modified transient plane source method. We're very interested to understand how the nanolubricant affected various base oils and fully formulated commercial products. Once this data was collected, we conducted real-world engine tests to see if the test methods we used were representative to real-world friction reduction in a combustion engine. As you know, there are many variables that can affect an additive's ability to protect a surface from wear and reduce the coefficient of friction, and you'll see from the data that the results were not always what we expected. We use the above test methods to evaluate the nanolubricant in 3 types of base oils, including Group 3 and Group 4, and also bio-based base oils. Our thought was to get a good baseline with the nanolubricant without any competing additive technologies present. We then evaluated engine oils, gear oils, transmission fluids, and started our testing in greases and hydraulic fluids. The test fluid that we used is a 3-part mixture of 1% by weight carbon nanolubricant, PAO ester base oil, and a proprietary Group 5 ester, which we will generally refer to as nanolubricant in this presentation. When evaluating base oils, we used the 4-ball test method 4172A and B, and both methods are 60 minutes, 1200 RPMs, 75 degrees C. And the only difference between the 2 methods is that the B method has a heavier load of 40 kilograms versus the 15 kilograms with method A. And all the oils retreated them with a 5% concentration of the nanolubricant. We discovered an 8.1% decrease in friction with the Group 3, a 12.8% reduction with the Group 4 base oil, and the bio-base oil gave us a wear scar reduction of 11.9%. We then conducted HFRR tests and found that in a Group 3 base oil, we reduced the coefficient of friction 18.9% with a 1% treat rate of the nanolubricant, a 23.7% with a 2.5% treat rate, and then finally a 30.2% reduction when we raised the treatment to 5% of the nanolubricant. We chose not to go to a higher percentage due to the fact that above 5% becomes less economical. The Group 4 showed similar coefficient of friction reductions of 20% with a 1% treat rate of nano, 22.9% with a 2.5% treat rate of the nano, and a 30.9% with a 5% treat rate of the nanolubricant. Wear reduction also proved similar results. In a Group 3 base oil, we witnessed a 23.4% reduction with a 1% treat rate of the nano, a 26.1% reduction with a 2.5% treat rate of the nano, and then finally a 31.5% reduction with a 5% treat rate of the nanolubricant. The Group 4 base oil showed a 17.4% decrease in wear with a 1% treatment of the nanolubricant, a 22.6% decrease in the wear scar with a 2.5% treatment of the nanolubricant, and then finally a 31.2% decrease with a 5% treat rate of the nanolubricant. We chose to do another set of HFRR using longer test conditions after we learned that the nanolubricant sometimes needs 30 minutes in an engine to fully realize the best results. In this test, we raised the time from 75 minutes to 120 minutes, increasing the frequency from 20 to 60 Hz and lowered the test load from 1,000 grams to 200 grams. We witnessed better results with the coefficient of friction with the modified test conditions, but slightly less on the wear reduction at the 5%. The Group 3 base oil provided a 45.4% decrease in the coefficient of friction, and the Group 4 provided a 38.7% decrease in the coefficient of friction. The wear reduction was 27.9% for the Group 3 base oil and then 17.5% for the Group 4 base oil at the 5% nano concentration. Now that we've established some baselines of performance with no other additive interactions, we moved on to motor oil. Later on in our presentation, you'll see how the motor oil data correlated to real-world conditions of fuel economy and engine power on the dynamometer. We started with a 4-ball test data using the ASTM 4172B method, which is the 60 minutes, 75 degrees C, 1200 RPMs, and a load of 40 kilograms. We tested a conventional 5W20 passenger car motor oil, a conventional 1540 heavy-duty engine oil, a semi-synthetic 1540 heavy-duty engine oil, and then finally an experimental 0W8 PAO-based passenger car motor oil. The results we discovered were somewhat unexpected. It should be noted that the data presented here was run 3 times, and any data that was outside the upper and lower control limits of the test was retested. The 5W20 passenger car motor oil had a decrease of 9.72% on the coefficient of friction and a decrease of 17.2% on the wear scar. The conventional 1540 heavy-duty engine oil gave us a coefficient of friction increase of 6.78% and virtually no change on the wear reduction or wear scar. In this formulation, some surface interactions seem to have affected the performance in this particular test compared to the tests we conducted with base oils. The semi-synthetic 1540 heavy-duty engine oil gave us a coefficient of friction reduction of 41.1% and a wear scar increase of 14.7%. And lastly, on the PAO 0W8 passenger car motor oil, we witnessed a 41.5% decrease in the coefficient of friction and a wear reduction of 57.2%. Now let's look at the HFRR for these same oils and see what correlations exist. The conventional 5W20 passenger car motor oil showed virtually no change in the coefficient of friction and a minor change on the wear reduction at 4.68%. The conventional 1540 showed a 7.94% reduction in coefficient of friction, but then showed a 10.7% increase in the size of the wear scar. If you remember, the 1540 was our outlier in the previous test as well, with no change in the wear scar and a 7% coefficient of friction increase. This is a point we need to do more testing to understand. The semi-synthetic 1540 showed a 4.24 decrease in coefficient of friction and a 13.3% reduction in the wear scar. On the 0W8 passenger car motor oil, there was a negligible change in the coefficient of friction and also a negligible percent change in the wear scar at less than 1%. After we completed this round of testing, we had some questions. Ultimately, our goal was to determine in the lab the probability that the nano lubricant could deliver real-world performance. We found an SAE paper that outlined the following test conditions and showed a correlation to real-world fuel economy, so we decided to do some testing using these modified conditions. And those test conditions are 75 minutes, 130 degrees C, 20 hertz frequency, 1,000 micron stroke, and 400 gram load. In previous real-world testing, we achieved a 4% increase in horsepower with the conventional racing oil, so we started our lab testing with the 50-weight conventional racing oil. Our testing showed a 1.54% decrease in the coefficient of friction and a 6.03% reduction in the wear scar for the 50-weight racing oil. Next, we tested the conventional 15W40 heavy-duty engine oil and the semi-synthetic 15W40 heavy-duty engine oil with the 400 gram load in 75 minutes, and the results correlated pretty closely to the previous test conditions of 40 kilograms and 60 minutes. The coefficient of friction on the conventional 1540 started at 0.150 and reduced to 0.144, which equals a 4% reduction in the coefficient of friction. The previous test with the different conditions showed a 7.9%, so the results were pretty close. On the wear scar, we saw a 1.9% reduction, but in the previous test, we saw an increase of 10.7%. Then on the semi-synthetic, the coefficient of friction showed a 5% reduction versus the 4.2% in the previous test, and a wear scar reduction of 17.2% versus 13.3% in the previous test. Next, we ran the mini traction machine with a slide to roll ratio of 20%, a load of 35 newtons, and temperature of 100 degrees C to understand how the nano lubricant compares to traditional friction modifiers and passenger car motor oil. The graph's a little difficult to see, so we broke out the data at 4 different points on the curve. We ran a traditional 5W30 passenger car motor oil without friction modifiers and compared it to oils treated with traditional friction modifiers and then to a 2% treatment of the nano lubricant in the baseline 530 passenger car motor oil. As you can see, at 100 RPMs is where we see the biggest difference. The base started at 0.034, then decreased to 0.033 with the traditional friction modifier added, and then it continued to decrease to 0.028 with the addition of nano instead of the traditional friction modifier. The nano was added to the base oil without the friction modifier. At 250 RPM, we see that the nano starts to perform at the same level as a friction modifier in the engine oil. This trend continues through the duration of the test. We then ran a second test at a higher temperature to better understand how the nano lubricant compared to traditional friction modifiers. The first test was run at 100 degrees C, and this test is run at 125 degrees C. Again, we see the most notable difference at 100 RPMs. The base started at 0.043, then decreased to 0.042 with the traditional friction modifier added, and then decreased to 0.034 with the addition of the nano instead of the traditional friction modifier. Then at 250 RPM, we again see a difference that we didn't see in the previous test. We started at 0.021 base, decreasing to 0.018 with the friction modifier, and then reaching 0.016 with the nano lubricant added. Around the 500 RPM mark, we start to see the friction modifier and the nano perform at the same level. Next, we looked at gear oils, starting again with the 4-ball test using method ASTM 4172B. We tested a conventional 80W90 as the baseline and then added 5% nano. Test conditions were 60 minutes, 75 degrees C temp, 1200 RPMs, and a 40 kilogram load. Our testing showed that the coefficient of friction increased slightly from 0.060 to 0.068, which represents 11.7% increase. But the wear reduction testing showed a base wear scar of 530 and then reduced to a 264, which equates to a 50.2% decrease in wear. Again, this is an unexpected result we need to explore in more detail. The HFRR data was run at 75 minutes, 60 degrees C, 20 Hertz, 1,000 microns, and 1,000 grams of load. The conventional 80W90 gear oil produced a coefficient of friction of 0.111 for the baseline and 0.097 after the 5% nano was added. This represents a 12.6% decrease in the coefficient of friction. The wear scar was a negligible difference from 299 versus a 302. On the PAO 75W90, we had no difference on the coefficient of friction at the 0.101 level and a small reduction in the wear scar. The data showed a baseline of 223 microns and 209 microns after the 5% nano was added, which represents a 6.28% reduction. Following represents some additional testing that's begun on greases, transmission fluids, and hydraulic fluids. The first test was on a number 2 calcium sulfonate grease with a weld load rating of 800 kilograms. The grease was tested using D2266 to determine 4-ball wear scar. The baseline scar was 0.55. With 5% nano, the scar was reduced to 0.40, which is equal to 27.3% reduction. The Timken OK load test had a 55 for the baseline and 65 after the 5% nano was added. This testing represents approximately a 15% increase. We are continuing to explore this application to understand what impact the nano can contribute to grease formulations. Lastly, we've begun wear testing on hydraulic fluid. This testing was conducted on an ISO 46 synthetic hydraulic fluid with the following conditions. This was an 8-hour test, 60 degrees C, 20 Hz frequency, 1 millimeter stroke, and 200 grams. Testing under these conditions yielded a baseline wear scar of 454, which was reduced to 424 after the 5% nano was added. This represents a 6.6% reduction in wear. Another area we're investigating is the merits of the nano lubricant enhancing thermal conductivity of a fluid. The following data was obtained using the modified transient plane source method for thermal conductivity. As you can see, the tests were conducted at 25 degrees C and 105 degrees C with different results. What we learned from this test is that the nano lubricant does affect thermal conductivity, both in a positive and a negative way, at the 2 different temperatures. This is just the starting of investigating the effects in this area, and we'll continue to do testing to understand the dielectric constant change and the heat transfer coefficient calculations for this material. So in summary, we learned that in various base oils, the nano lubricant gave us a consistent reduction in friction and wear using both the 4-ball and HFRR methods. Then when we switched to motor oil, the 15W40 heavy-duty engine oil gave us some unexpected results compared to the base oil numbers. We learned then from the MTM that the nano works better at startup or lower RPMs and then tapers off during increased RPMs. And also we learned that temperature affects what RPMs that effect starts to taper off. We need to continue to investigate different test conditions to fully understand the potential of nano lubricants, but so far the tests look very promising. That's the conclusion of our testing data. Now we'll transfer over to Chris to talk about our real-world data.
Thanks, Kevin. After seeing promising results in the laboratory, we decided that we should do some real-world testing before we spent more money on laboratory testing. So we took the product and put it into a FedEx step van. In this case, we contracted with the Ohio State University Center for Automotive Research to check for fuel economy before and after the treatment had been applied. Using their dyno that was designed for large trucks, they were able to document a 3.59% increase in fuel economy. This was encouraging, so we moved on to a Dodge Ram 2500 with a 6.7-liter Cummins engine. And we wanted to determine how much horsepower gain we can get. In this case, we had to run 5 passes with the dyno to get a baseline, which in this case it was 460 horsepower. And then we treated the vehicle and ran it for 5 more passes to see what the difference was. After the product was introduced, we ended up with 478.42 horsepower, which was a 3.79% gain. We also got a 2.95% gain in torque. From there, we moved on to a passenger car, thinking that the product should work in any kind of engine. We used a 2014 Nissan Rogue, and in an over-the-road test, an extensive over-the-road test, we were able to take the fuel economy from 40.2 miles per gallon to 41.9, which was a 4.23% gain in fuel economy. So from there, we moved on to a motorcycle to see what effect we would have on a motorcycle as far as horsepower. And in this case, it was a Harley-Davidson, a 2014 Harley-Davidson Street Glide. And putting it on the dyno, we were able to document a 3.3% gain in horsepower and a 3.2% gain in torque. So the last engine that we could think of that would be worth testing would be a yard equipment, small engine type of test. In this case, we got a Kohler engine on a Gravely ProMaster. The way we tested it here is that we put the lawnmower on a dyno and weighed how much gasoline was being added so we can see when it would run out of gas. And in this case, we documented a 2.75% increase in fuel economy after the engine was treated. So as you can see, the results in the lab did translate into real-world testing. Our next step in testing will be to test brand new engines. We realize that all the testing we've done have been on used engines, and we're not sure how much of the results are restoring lost power due to the age of the engines. We were able to notice a direct correlation between the HFRR test and the fuel efficiency gains that we were able to achieve. The better the HFRR, the better the fuel efficiency gains. Now I'll send you back over to Todd for our closing remarks.
Thanks, Chris. Here are some things we'd like to learn more about. For example, we'd like to learn more about how the nanotechnology performs in grease and organic friction modifiers. We also need to do some more testing with bio and metalworking fluid and hydraulic fluids. Some of the additional findings we have are rate of oxidation of motor oil slowed considerably with the addition of nano. Total base number in diesel engine oils has been sustained over a longer period with the addition of nano. These are items we would like to study more in the future. So in summary, we have shown clarity issues solved, suspension issues solved, reduction in wear, reduction in the coefficient of friction, and lower treatment ratios needed to achieve these results. As you have seen, new nanotechnology allows for wider uses across multiple applications. Thank you for joining our presentation today. Please don't hesitate to reach out to us for further information or if you have more questions.